So in this video we will talk about the concept of distinguishability, and we will apply this concept on a set of palindromes. Okay, so let's start with the definition as usual. So if we have I with a set of symbols, usually I is what? Usually I is just 0, 1, but it can be any finite set. And then let L is a subset of I star. So I star is the set of all the combinations of strings we can get from concatenating each symbol of I. So obviously this is an infinite set. It's a subset of I star. Then we say that L slash X, this is equal to all the symbols Z such that X, Z is a subset of L. Okay. So in other words, if L is 0, 0 and 1, 1 and X is just 0, then Lx, this is equal to 0. Why? Because 0 concatenated with 0 will take us inside the set L. Okay, so now if we have two strings x and y which are distinguishable with respect to L, which means that when do we say that they are distinguishable with respect to L? When L slash x is not equal to L slash y, otherwise they are indistinguishable. Okay, and a string z for which one of x and y is in L and one of the other one is not in L is said to be distinguishing x and y with respect to L. Okay, so in other words, let's demonstrate it using a picture. So let's say this is my I star, okay, and this is my L. Okay, let's say this is my x and this is my y. So this is my x and this is my y. If I concatenate y with z, let's say I reach here, and if I concatenated x with z, I reach here. Okay, now concatenating x with z ends up, and concatenating y with z ends up outside L. So this means that x and y are distinguishable. Okay, distinguishable. Okay, so now let's see another example. Okay, so now L is a set of all strings ending at 0, 1. Okay, so then we have x is equal to 1, 1 and y is equal to 1, 0. Are they distinguishable with respect to L or not? Okay, so x is 1, 1 and y is 1, 0. Now can we find a z for which xz is in L and yz is not in L? Can we do that? 1. So this is my z. And then y, so this is xz. xz. Then yz, this is equal to 1, 0, 1. So now this guy is not in L, but this guy is in L because it ends up with 0, 1, right? So this means we have found a z for which we have xz not in L and yz in L. So this means they are distinguishable. Okay. Now let's talk about 1 and 1, 1. Are they distinguishable with respect to L? So x is equal to 1 and y is equal to 1, 1. Now note that in order to make this guy inside L, I have to write something and ending up at 0, 1. So whatever z I choose, that has to be ending up at 0, 1. Okay, so this means that if I choose a z which ends up at 0, 1, then both of x and y will be in L. If I choose a z for which does not end up at 0, 1, then both of x and y will not be in L. So this means that they are not distinguishable. See what is the relationship of distinguishability and the finite state automaton. So now note that if we have a finite state automaton M, which is always represented by S, which is the set of states, I, which is set of in which the input symbol, F, which is the mapping, S0, which is the starting state, and F, capital F, is the set of final states. So then we say that if X and Y are distinguishable with respect to the language recognized by M, then we say what? We say that F of S0X and F of S0Y cannot be the same. Okay, so in other words, if I start with S0 and traverse the string X, I should land at a different state than if I started with S0 and traverse the string Y. Okay, so what does it mean? So let's say proof here. So we say let F of S0X, this is equal to Sx, and F of S0Y, this is equal to Sy. Okay, so then, and also we say that since they are distinguishable, so without loss of generality, we can say xz belongs to L and yz does not belong to L. You can choose the other way around as well. Okay, so then what is F Sx z? Does it belong to L? Does it belong to F? Yes, it belongs to F because we have xz, a member of the language. When it's a member of language, then it means that when we have X, we start with S0 and traverse X and reach Sx. So from Sx, if we go to from Z, if we take Z, we have to end up at a final state. And similarly, we can say F of Sy Z, this does not belong to F because Syz is not in L. Okay, makes sense. So this means what? This means what? So this means that F of, since Z is the same string, so since using the same string lead us to a different states, so this means we can say Sx is not equal to Sy, which means that F of S0 X is not equal to F of S0 Y. Okay, so this completes the proof. Okay, now we talk about the minimum number of states for an FSA. So now let's say that we have, this is I star and this is our L, and we have, this is some set. So this is some set, and this has a property that it has n strings such that every pair is distinguishable. Okay, so again, this is my I star, which is the vocabulary found by the input symbol. This is my L, and this is some set which has a property that n strings, it has n strings such that every pair of those n strings is distinguishable. So can we say something about the finite state automaton that recognizes L? Yes, we can say that, because we can say what? So it has n strings. So this means what? It means that every pair corresponds to different states. We can say that. Why? We can, for example, the strings here are x1 up to xn. Then we know that f of s0 x1 and f of s0 xn, they all are different. Why are they different? Because what we, okay, so they are different. So they are different because of what we did right here. Okay, so when they are different, then we can say that the finite state automaton recognizing L must have at least n states. Okay, so if we can find, note that this set can have some overlap with L. That is not the point. The point is that if this set has some property, which is this one, that n strings, for n strings every pair is distinguishable, then this distinguishable with respect to L. Remember that this is important. Distinguishable with respect to L, then this L must have at least n states. Okay. So now we turn our attention to a set which is the set of palindromes. What is palindromes? Palindromes is the set of strings which are read the same way forward and same way backward. For example, we have the palindromes can be written as like this. So we have 0 and 1. Okay, then 0 0 and 1 1, because you can read 0 0 from left to right and right from right to left the same way. And similarly we can write 0 1 0, 1 0 1, 0 0 0 and 1 1 1. So these are also palindromes because they are read in the same way forward and backward. And then we can say here for string 4 1 0 0 1, 0 1 1 0, and then we can say 0 0 0 0, and we can say 1 1 1 1. So, and we can carry on. Okay, so now we have to prove that a set of palindromes is not regular. So how do we go about it? Okay, so then make use of this property here. So we can say if n, and then we can say can we find n strings of the above property. So I'll have a big arrow here. Okay, so if n is 2, for example, so if n is 2, then can we find that they are distinguishable with respect to this? Yes, we can find, because we can find uh, 0 0 and 1 1, and they are distinguishable by 0. So z is equal to 0. So this means we can find two strings which are distinguishable with respect to the set of palindromes. Why? If z is equal to 0, so let's illustrate it a little bit more. If z is equal to 0, then 0 0 0 is in L, but 1 1 0 is not in L, right? So now can we find the same story with n is equal to 3? Yes, we can find it. We can say 0 0 1 1 and 1 0. Okay, now for 0 0 and 1 1, we already know that z is equal to 0 works. For 1 1 and 1 0, we have to be careful. So we can say for 1 1 and 1 0, z is equal to 1 1 will work, because 1 1 1 1 is in L and 1 0 1 1 is not in L. And similarly for 0 0 and 1 0, for 0 0 and 1 0, z is equal to 0 will work. Okay, because 0 0 0 is in L and 1 0 0 is not in L. So similarly, uh, let's do 6. Okay, for 6 we can have any length 3. We can choose any length 3: 0 0 0 0 0 1 0 0 1 1 1 0 0 0 0 1 1. So then these 6 are actually they have this property that every pair is distinguishable with respect to the set of palindromes. So let's choose any of them. So let's choose 0 0 0 and 1 0 1. Okay, so we can say 0 0 and 0 0. So now 0 0, if you choose z is equal to 0 0, then this guy is in L and this guy is not in L. Now choose, let's say 0 0 1 and 1. Okay, so then 0 0 and 0 0. Again, this will make our life easy. Okay, so this one is in L and this one is not in. Why is this in L? Because if we can read it left to right, then we get the same string, and we read it from right to left, we get the same string. So as in a summary, So if, for example, we have any n between 2k plus 1, 2 to the 2, if we have n between these two numbers, for example, 2 to the k plus 1 and 2 to the k plus 1, then choose any of the k plus 1 length strings. Okay, and we can actually, by inspection we can see that they are distinguishable pairwise. So this means that we can find any n for which we can find this property that each pair is distinguishable with respect to palindromes. What does it tell us? So this means since n is n, there is no limit to n. This means the corresponding FSA will have infinite states, right? But FSA is finite state automaton. So this means no FSA exists for L. And what does our Clean's theorem says? So Clean's, it says L is not regular. Okay, so due to Clean's theorem, we know that a finite state automaton only recognizes languages which are regular. Okay, and all regular languages can be recognized by finite state automaton. Okay, so as a recap, what we did today was we introduced the concept of distinguishability, and we see how a finite state automaton is related to distinguishability, and then further we said that can we find a minimum number of states for an FSA for a finite state automaton using the concept of distinguishability, and then we applied this concept to a set of palindromes. Okay, so hope it was beneficial for your cause, and hope it was easy to understand. Thanks for watching. Hope you like the video.